right on time. Thanks everyone for joining this session. Today we'll be talking about AI. That's a hot topic. Hope you'll enjoy it. So first of all, we all hear those terms: AI, neural networks, LLMs, ChatGPT. It's often used interchangeably, although reality is that those are very, very different terms. So just to level set this conversation, AI is a computer science field. It encompasses all sorts of algorithms, and it's a big, big, big topic. While neural network is just one set of algorithms that's used in AI. LLMs, they utilize one of those set of algorithms, mainly transformer models, and they are now they have recently taken the world by storm. While ChatGPT is just an interface that accesses one of those LLMs. So you may hear people, experts, using those terms interchangeably because that's how the public understands them, but those are very, very different fields. Okay, so let's talk about large language models. What is really large language model? In reality, large language model is just two files. One file is parameters, and the second file is a neural network that uses those parameters to actually predict the next word and produce output. So you just need 500 lines of code to run that neural network. You point the binary to the parameters list, and you can run it on your local computer. You don't need access to the internet. You don't need anything other than those two files. Actually, running that neural networks is relatively compute cheap. So you don't need a very powerful computer to run that neural network, or as in data science space we call infer the next word, predict, basically. One important thing to mention here is that there is a distinction between open models and proprietary models. This talk is based on a paper that Meta has published. So the reference here is made to Llama 2 series. Meta released a large language model with certain sets of parameters: 7 billion, 13 billion, 34 billion, and 70 billion. When you run that neural network, the difference between those parameters is the time to output. So you can think of it as, if you're running a 7 billion model, parameters model, it will run roughly 10 times slower than a 70 billion parameters model. Nonetheless, you could still run it on your local computer. You don't need internet, literally you need nothing other than your computer. So how are those parameters obtained? Since we said that this is the crucial point of the large language model, we actually need these parameters to run the network. They're obtained by training the model. And to train that model, there's a public information on Llama. Since it was the paper is available, Meta has made it all open. It was trained on 10 terabytes of data, roughly. So you can think of it as you take 10 terabytes of data from the internet, preferably quality data. Then you procure a cluster of roughly 6,000 GPUs, and those are not normal processors. Those are NVIDIA N100V. Those are very expensive processors. They cost between $20,000 and $100,000. Then you run a training on that data set to get the list of parameters. And that roughly costs $2 million, takes 12 days, and then you end up having a list of parameters. So in that case, 70 billion parameters model would take 140 gigabytes of data, since the data type is float 16. And you can think of these parameters, or you can think of how this was compressed into 140 gigabytes of data as a compression of sort. So the difference between compression that you're very familiar with, like zip or rar, is that this is a lossy compression. What it basically means is that the model understands the form of the language. It does not exactly know, but verbatim, what data it was trained on. It understands what should come next, but as said, it is a lossy compression. So it understands the gestalt of the language, so to speak. So what does this neural network really do? There is one task that this neural network is optimized for. It knows how to predict the next word with high accuracy. And the way those large language models work is that you continue to feed in the next word that was predicted into the input layers of that neural network, and then again it predicts the next word. And that's how you loop it, so they, at each time, each second, each millisecond, you get a next word. So you can rather think of it as a machine that predicts the words so accurately that it actually creates compelling materials. So again, one thing that this neural network does is predicting the next word with the highest possible accuracy. What does this really mean? It means that this neural network has to really understand the world. It has to learn about the world. In this example, you see a Wikipedia post with blanks in that text. So for neural network to really predict those words, it needed to learn who Ruth was, where she lived, when she was born, what her husband's name was, where she worked, what she was known for, etc. So neural network, to perform its operation, had to actually really understand the data set and what that really means. Because to predict accurately, you really have to understand the content. So how does it do it? We don't really know. We are not 100% sure, but there's a lot of things that we know. So what we do know is the entire architecture. Those transformer models are very well understood mathematically. They are very well understood algorithmically. So we know all of the algorithms that go into building such a neural network. What we don't understand is how those billions of parameters cooperate and collaborate together to get us that prediction, that next word prediction. We also understand how to optimize those parameters, so we know how to teach the neural net to predict that next word. We know the algorithms. The crucial seminal algorithm is the backpropagation that actually modifies those parameters to get us to the highest accuracy possible in the next word prediction. There is this viral example, no longer actually you can check it yourself, but a month it was already fixed. But to show you that this knowledge that that large language models possess is quite weird, you would ask ChatGPT, so GPT-4 model, just a month ago, who is Tom Cruise's mother? It would tell you Mary Lee Pfeiffer, but when you asked it who is Mary Lee Pfeiffer's son, it wouldn't know. So it shows you that this knowledge that the large language models possess is quite weird. That's still not fully understood and explained how those parameters really understand the world around us. Okay, so you roughly know by now how to build that base model, how you train this base model that was based on 10,000 terabytes of data. But if you ask that base model a question, it will give you more questions. So the base model is not really useful. Like, the base model does not know how to answer questions in a way that humans would do. There is another step in this process that's called fine-tuning, which we need to use to get us to a state where we have a large language model that can actually be helpful in business applications, in day-to-day work, in day-to-day life. For it to be useful, we need to train what's called an instruct model or an assistant model. And to do that, what we need to do is now swap this data set from 10 terabytes of large quantity of data to more quality data. And that quality data that we use, those are actually human-written instructions that we teach the model on. So you can think of it as we get hundreds of people, we ask them write questions and answers to your own produced content, and based on that we swap this data set, we retrain the model again on it. Roughly you need like 100,000 conversations, and we rerun exactly the same optimization. So what I'm generally saying here is that you take each one of us here, we ask you to create questions and answers that are of high quality in the field that you are aware of very well, and you can guarantee that this content is correct. Only then, after we retrain the model, we can start using it as a useful assistant. And this process of creating the data set that is has really good quality, it's more and more used. It's a cooperation of human and machine. Since those models are getting more and more advanced, right now, rather than writing it purely by a human, humans actually ask it a question and pick choices from the content generated by those models, and they put it all together into one data set and then retrain those models. That part of training, which is called fine-tuning, is generally less compute is needed for it. So we can do it more often. So that fine-tuning part of training large language models can be done at companies even weekly. I showed you the numbers for Llama, $2 million, 70 billion parameters, roughly trained for 12 days. You may think that it's a lot, but the reality is that those are rookie numbers right now. You should multiply it by a factor of 10, roughly, to understand what the state of the art really is right now. So we are talking about $20 million or north of $20 million to train the base model. While fine-tuning is much less costly, so you can do it every week, basically. Which means that if you spot a recursal curse that I showed you before, like if you spot an error in large language model, you can easily iron it out by actually fine-tuning. So that's how those models get better and better. So think of it as you do once a year the base model, you train it on a large data set, and then you fine-tune the model every week, roughly, on way more quality data based on your specific use case in your organization. Okay, so let's switch gears now, and let's talk about how you get to use these models. Some of you have played with BART, with Vertex AI, with other tools, with open source models. So you all probably have seen those parameters like top K, top P, temperature, token limit, greedy sampling, random sampling, and such. So let's briefly touch on what those mean and how they impact what is being generated. So first and foremost, the difference between greedy sampling and random sampling generally causes the model to either answer the question exactly the same way, or in a manner that each time you ask a question you get a variety, a bit of a different answer. So if we chose greedy sampling, that would basically mean that the model would always go with the highest predicted word, and it would always answer exactly the same way. While if you go with random sampling, this is where you get different responses. This setting is not always available in products, because obviously the producers, the vendors, they want the answers to be different each time you ask the question. So you may not have the ability to actually switch between greedy and random sampling. Top K versus top P sampling. This provides you an ability to define to choose the distribution from the probabilities distribution. Basically, if you set top K to 3, each time the model makes prediction of the next word, it will only select from top 3 highest probability words. While if you define top P as 30%, it will take the words that cumulative probability is not higher than 30%. Temperature defines actually the creativity of those large language models. You may think like, why do I even care about those parameters? Depending on your use or your need for use in those large language models, you may care because it directly impacts what the output will look like. So if you want the model if you're using the model in creating haikus, or you're using it for more creative purposes, art, writing a novel, anything like that, then you would go with a higher temperature. You would go over 1, basically. The temperature parameter, it's quite remarkable because it changes, it alters the probability distribution in the prediction of the next word. So if you go with setting 1, what it basically means is it's leaving the probabilities as originally in the neural network as in the parameters. While if you go below 1, it changes those probabilities such that you get more precise answers. The probabilities is more strongly picked. And what it means for you, you can think of it as, you're talking to a very very strict person who always gives you the most precise answer. So below 1, it's a very strict person, while above 1, it's this creative, it's your uncle at the dinner table who always cracks jokes and such. So who's the best? Who is the best in this market, LLMs market right now? You can see that the proprietary models are leading the pack because they are the most funded, they have the largest models, they have the largest data sets, and that ranking was created by pitting models against one another. So you would go on a Berkeley's website, you would pick the answer that the model generated, and based on which of those models got the most scores, that list was created. So you as a user, you wouldn't know which this which model this answer was coming from, but the ELO score, which is the ranking based on, shows that as of right now, we see proprietary models leading the pack, then open source models following. Why would you care? Because open source models, they have the paper available, they have all of the architecture is public, while those closed models, we don't really know what they were built on. We don't really know how they work. So what caused those large language models to become so big right now? Why is everyone talking about large language models, and why didn't that happen before? So there is one factor that actually enabled this revolution, and that was a discovery or observation that if we increase number of parameters and we have larger data set, we can expect more intelligence for free. So this was an observation as researchers worked on it that generally told us that for us to have a better model and better prediction, better accuracy of the next word in this prediction, we just need more compute basically, because we can always get more data. So that's how this whole, we could confidently say that with more data, we get much better accuracy in terms of predicting the next word. Why do we care about accuracy of that prediction? Simply put, because it has also been observed that with higher accuracy, when we evaluate those models on tasks like bar exam, we could get from 10% pass rate, 10% at bar exam, to 90%, and various other evaluations, health exams, all sorts of other things that we use in our day-to-day life, they have gone up extensively. So that's an example of GPT 3.5 going from 10% to 90% when GPT 4 came out. So now let's switch gears and let's do a very brief, demo of how those LLMs can be used in business applications. So I asked it to collect information about Sabre, recent stock price, and organize the that stock price into a table. So it basically did that for me. But as I told you, large language model can be run offline. Those are really two files that don't have any access to the internet. So what happened here is that actually ChatGPT went out, grabbed data from the internet, so it used the browser, and it collected it in a table. What it basically means is that those large language models, they understand that sometimes they need to use a tool. It's like you and me. When we do something, we sometimes go grab a computer. We do something with that computer so that we can produce the end result. It does not always have to be the large language model that has all the data. It goes out and uses a tool. Okay, so next thing I asked it, okay, add the predicted value column to the table, use a factor of 2 to predict the value in the newly created column. And it again created another column, added another column, and multiplied by 2 as I asked it to. So in this example, yet again, large language model went out, took a calculator, used the calculator, and then provided you the result. Yet another example, organize this into a 2D plot. The x-axis is the date, the y-axis are the values of previous close, open, bit, asks, and asks. And it created that plot again. So how did the large language model plotted something if it does not know how to plot? So what it did, it actually converted that question into Python code. It ran that Python code in a local environment, and it interpreted the code and gave you the result of that interpreted code. So again, it used the tool. It did not do it all by its own, it did it with a use of tool. So now let's add a linear trend line to this plot. And it added linear trend line, exactly the same process. It used it converted the ask to Python, it ran it in an interpreter, and the result of this interpreted code was this added trend line. So now I asked it to generate a picture that tells Sabre's story based on the information that were gathered along the way. And it created a picture. So again, in this example, it wasn't the large language model itself creating the picture. It was the large language model using another neural network, in this example, DAL-E2, to generate that picture. And last example that nicely shows how those tools can be used in business applications is actually a picture from a demo that was made by one of the OpenAI co-founders last year, where I asked the model in here to read that image and convert it into a website. So simply from that image, ChatGPT or any other large language model, as right now Gemini models, Google models are at par with GPT-4, could convert it into a real website. That is a real website that actually worked. When I did that, I was surprised myself that it could actually not only write HTML but a JavaScript and then create that page where when you hit the reveal punchline, it actually showed what the punchline was. So in this example, large language model used another neural network to understand what was in the picture, and that neural net was a convolutional neural network that actually did all of it. You may have seen, you may have not seen, but those models are also voice enabled. They not only produce text to speech, but they also have speech to text models built in. So you can ask it a question, and they answer like a human being, hopefully. Huh?
Sure. Executed the command to add flowers to settings and details to.
Yeah. So basically, what it means is that those large language models are just the reasoning engines. They are the CPU. You can think of it as, for us, human beings, we use our reasoning, and then we apply this reasoning to a variety of tasks that we have at hand. So let's talk about the future of LLMs. What are researchers really thinking about right now? One, and the primary focus right now of the research area is System 1 and System 2 thinking. This idea of System 1 and System 2 thinking was popularized by a book called Thinking Fast and Slow. So System 1 thinking is this intuitive, immediate answer. That's where I asked you what 2 plus 2 is. You know it's 4. It's what we sort of know. And this is what today's LLM actually have. They have this System 1 thinking ability. What they don't have is System 2 thinking. But researchers are already actually working on System 2 thinking, which is, when you go and think of, whether I should get a mortgage, should I actually go and take that job or take another job? Should I, is this love of my life? Those are the things that we don't know immediately answers to. We need time to actually, process this information. We take days, weeks, or months sometimes to actually arrive at a decision. And this is what those models don't have. Another sort of example is, speed chess. You go in and you play chess. You sort of, in speed chess, you have literally like seconds to get to the next player. You have to do it in seconds. While in normal competition chess, you take time to think through those decision trees, or you think through multiple choices. LLMs only have System 1 thinking right now. So basically the words that they predict, it goes chunk every single word. They roughly take exactly the same amount of time to predict the next word, but they don't have any System 2 thinking. So they don't really know how to convert time into more accuracy, which is what we would, as human beings, probably want them to have longer term, since we would be more safe saying that whatever they have predicted is actually correct. So now the research is going into the area of how to convert time into higher accuracy. So you can think of it, this diagram shows thoughts. So you may go to one of those LLMs in the future and you can tell it, hey, is this a good time to buy a house right now? Take 30 minutes. You don't need to answer right immediately. Just take 30 minutes and tell me what your idea is. And in 30 minutes, it would predict whether it's the right time to buy a house much more accurately than if it immediately gave you the answer. Another area of business use of those large language models is custom GPTs and App Store for GPTs. So all of these companies are now trying to create more variety in custom GPTs. So they are enabling all of us to build our own GPTs with our own data sets, with our own data we can feed into it, and they are trying to actually make it so easy that every single one of us can use it for our day-to-day purposes, for our work purposes. There's multiple initiatives inside of Sabre where we want to start using it for knowledge management, to get to the relevant answer very, very quickly. So to summarize, what are those LLMs going to look like in the future? You can think of it as a reasoning engine, as some type of an operating system that's navigating all of those thoughts that a large language model can have based on the answers based on the questions we provide. So it will have access to the internet, it has access to the browser, It has access to, it has its own context window. So it's like RAM in current computers, and those context windows in LLMs grow with time. It has access to other LLMs. It can pull data from other LLMs. It can read and write. It can create video, and it can understand video. It can also go and talk to other large language models, as mentioned before. So in short, those large language models are becoming more and more useful in our day-to-day life and day-to-day business. And longer term, we likely could foresee that they may become as efficient as human beings in many of those tasks, but they will have way more knowledge that we will never actually be able to get. Nonetheless, they are at our mercy. So basically, we control those large language models. They have not gone beyond human. They are based on our data, the data sets that we create. At this point, they have no way to self-improve. So irrespective of what the media are telling us right now, the risks involved perhaps are actually less than what everyone may think about it. So with that, go explore and check it out, play with it, because the future is definitely, we can say with certainty that all of us within the next 3 years will be using it on a daily basis in our day-to-day work. And as you saw in the previous session by Łukasz, we are now starting to use GitHub Copilot, which is one of the products that is actually based on those large language models. Thank you, and with that we can turn to questions.